Graviton and I have done these spaces twice before. The first one was about quantum entanglement, and then the second one was just about black holes. Sort of highly recommend that you check those out and have a listen. But we've just been sort of investigating some of the paradoxes in physics that I think sometimes appeal to everyone, because no matter what your sort of physics background, everyone can appreciate a good paradox. And so for me, yeah, the dark matter is one of the big ones. I mean, some of the assertions are sort of outrageous, if true, and we have to always sort of approach it with an open mind and consider that some of the things that we discuss are sort of right on the cutting edge of physics and still are open to interpretation. A lot of the measurements are not in the sense that the measurements are repeatable, and you can get quite accurate data. But in terms of the how and the why, we sort of always, well, I tend to always keep an open mind for that sort of stuff. So yeah, I guess one of the.
So I think that's probably a good place to start, and I think that there were some things that so a little points of clarity from the last time, and I think so. We were talking about the role of theory, and we kind of went all over the place last time, right? But
Yeah,
kind of
yeah,
the role of
hilarious.
theory and experiment, right?
Yeah.
I mean, observations rule the day.
And it has to be backed up.
It has to be backed up. And so the theoretical frameworks are used to explain the experiment. And sometimes there are consequences within the mathematical construct of the theory that you may not like, or I may not like. But if the data supports the observation, then you pretty much have to say, well, I don't have any physical basis to rule this out yet, without invoking some type of conjecture or something of that sense, or or maybe there's a particular no-go theorem that's preventing nature to behaving that way. But I'm not a string theorist, and I have criticisms of string theory. But if string theory ends up 10 to the 500 stable vacuum, I kind of balk at that kind of discussion. But if it ends up being that we can find a de Sitter vacuum that's stable and emits solutions, then you start have to take those things a little more seriously, because at the end of the day, the data and these precision measurements that people make kind of rule the day. And so
I agree 100%.
Right. And so then but there are certain cases that you can eliminate, like if you have a tachyonic signal in your, or mode in your theory, that's which would indicate faster than light travel, then you could say, well, if I take localities seriously, then I have to eliminate that. But anyway, and then
I sort of sorry, so go ahead.
Go ahead. Well, I was going to say the other thing is that when scientists are generally presenting all of these ideas, Penrose, Nema, Brian Greene, whatever, which Brian Greene is kind of more of a popularized scientist now. But I mean, these various views, and then and Sean Carroll, and you try to mesh them together. It doesn't work that way. They have particular frameworks that they're working in. And when you try to say, well, I like this piece of this piece and this piece of that piece, you may not be able to put them together in some logical form, structure. But anyway.
Yeah. So I'd agree with that. Some of these, theories can be competing ideas, but I think that's part of the scientific method, is that, we have to be sort of courageous in science, where we have to entertain competing theories, and then we let experiment decide. So
Right.
it's like it's okay to question science, and that's exactly what science is the ability to question your framework and to accept new data and reject your framework. It's if the new idea is found to be more accurate, more repeatable, and agrees more with measurement in more cases, then we will just reject the previous consensus and adopt the new one. So we don't have, that's one thing that is, very fundamental with science. So
Right. And
I think
the
it's a
other
good
thing
idea
is
to keep by things. Yeah.
yeah. The other thing is that science is falsifiable. Mathematics is provable in so much that, and sometimes I will use the words theorem, but when I'm using the words theorem, I'm looking at it from a mathematical physics point of view, where you have
Yeah.
the formal structure, the formal mathematical structure, and you can make inferences based off of that, like the no communication theorem from quantum information from entanglement. For instance, that theorem and the proof of the theorem follow directly from the formal structure of quantum mechanics. And so science, the theoretical construct, the parameters surrounding those models, those various models, are falsifiable. And so we're always trying to reject the null hypothesis, which is the base theory. And so I think that that's an important thing to kind of get across. And, it's not some, there are unbelievable paradigm shifts and logical jumps that we make. But at the end of the day, we're still, little kids looking up at the night sky trying to figure out what's going on, and that's the beauty
100%.
of it.
Yeah, 100%, man. Yeah, that is the beauty of it. And like, it is one of those things where some of the scale of these, the vastness of the universe is what is hard for the mind to comprehend. And there might be limits to our human understanding, but we certainly have a good crack at it. But we have to have a little bit of humility to say, so bringing it back to the dark matter theme, is that, that they can basically make these claims that 85% of the matter in the universe is missing, and for that just to be normalized and just to sort of go, oh yeah, well, we've basically done rigorous scientific modeling on galaxies and things like that, and there's not enough mass to account for the behavior that we see, where these laws that work everywhere else don't seem to work unless we account for this missing mass.
Yeah, and so there's like two components of that missing mass energy, right? And that's the kind of the title of this talk that we're
Yeah,
going to
yeah,
be kind of going through. Dark matter, which is the
yeah,
smaller portion of the
yeah.
equation, and then dark
It's
energy.
almost like the dark matter. That's not even mind blowing enough. Like I've just said, 85% of the mass or matter in the universe is missing, and like that's not even the big part. Like, but no, keep going.
Right.
Tell me about dark energy. Tell me about dark energy.
Right. So yeah. So there's not a lot you can say. I mean, there's a lot that you could say, but we still don't know.
There's a
We've
lot that
have
we can conjecture. Yeah.
That's correct. I mean, I on both ends, on the dark matter parts and the and also the dark energy. I mean, dark energy appears to be a generalized property of the background of space-time itself. So it's the fact that it's the energy that space-time has, and it takes on a particular value, and that value is very important because it matches certain observations. The universe expanding, and not only expanding, but it's accelerating, which means it's being pushed out. Like space-time itself is being pushed out at a not at a constant rate, but at an accelerating rate, which was discovered when I was in college, and probably when you
Yeah,
were in
yeah.
college as well.
Yeah.
So, I mean, it's pretty exciting, and we should probably talk. I think, we've kind of got a limited time tonight.
Yeah, we should probably get to the juicy stuff as much as we can because we're limited time.
Right. So, you want to start off? Let's start off with dark matter, and
I think so. I think
see.
there's a logical progression there in terms of like the dark matter, the way that they sort of make these measurements on galaxies and clusters and things like that, and then they sort of they say, well, depending on the orbits and how much the motion of the galaxies at the edges, they should be able to estimate like how much mass is in there, and then it doesn't match with like I think the brightness, and
So
yeah, go ahead.
They first discovered, so the first observation of dark matter was studying these, it was in like the 1930s, studying the rotation of a few spiral galaxies, right? And so the velocity, when you look at the velocity as a function of the radius, it didn't quite match the expectations. And this is again, we started off last week in a kind of an exercise of not last week, but 2 weeks ago, as an exercise in what high school physics can show you. But this again is kind of high school physics level where you can calculate the radius. You don't have to assume on these kind of scales, you don't have to assume any fancy space-time metric where you're calculating, because that's a very difficult calculation. You can make approximations, and so you can calculate these velocity curves, what theory would expect, and what the observation actually is. And I shared up in the nest an example of that velocity curve. The expected velocity is much lower than what is expected, and so it led to the notion that there could possibly be interacting material in there, and it comes down to fitting the parameter on what would be the missing mass. And so that was in the 1930s, but still, this mass they can't see, so it's not light emitting, which is
so they can't interact with it. Yeah, they can't interact with it electromagnetically, I guess, is like, well, if you're talking about WIMPs, that's like one of the candidates, I guess, for it.
That's one of the candidates, but there's no so there's no scattering with photons.
Yeah.
And so it completely dark, which, from a particle physicist point of view, you're just like, what is that made out of? How does that work?
Yeah.
How did it attribute mass? What mechanism did it attribute? So it's a massive object.
Yeah. So that's a really interesting point, I think, because it's okay to have massless particles, bosons, that we see photons, and we measure these things, and we know that photons can be affected by the curvature of space. So gravity does affect massless particles. So there is already sort of like a precedent for understanding that. But it's this idea that these massless particles it's the energy in these massless particles are somehow making up for some of this missing mass. That's the sort of almost the paradox, because
they're massive particles. It's not that it's massless. They're
because the energy equivalence.
So the energy equivalence is very high, but they're slow. They could be passing through us with no interaction, or low probability interactions.
Yeah, so like neutrinos, for example, are just streaming through us all the time from the sun, or from everywhere. But our ability to interact with them is almost like probabilistically non-existent. So they have to have these, experiments set up a square. What is it? A cubic kilometer of array of photodetectors in Antarctica, and like. mine shafts and things like that. So they have them at these huge scales, and then they still only detect like a few neutrinos. So some of these particles could just be streaming through us at all times, but just not interacting with us electromagnetically. I guess that's the weakly interacting massive particle sort of idea. But neutrinos don't. They have a non-zero mass, but it's very, very small mass. So that's been proven that they do actually have a non-zero mass. But so they may not actually be a great candidate for WIMPs because they actually
there's potentially things called like sterile neutrinos that could be a candidate. I mean, I was going to get into this a little bit later, but the way that these particles interact via in the standard model, it could be another fermion field, but it's decoupled from. You would have basically a weak current, but not an electroweak current. That's basically saying that that doesn't interact with the electromagnetic spectrum. So the reason that it would pass through us, when for the audience at home, you clap your hands. Why don't your hands pass through through each other? It's the electromagnetic force.
Electromagnetic repulsion. Yeah.
It's the electromagnetic repulsion that's preventing that passage through. The neutrino has zero charge, and it's so there's a low cross section of interaction between the electron and the nucleus. So they're passing through you constantly, and they're emitted from the sun. But dark matter is different in that, one, we can't see it. Two, it's interacting with the mass. It interacts with the gravitational field via its mass, but it also passes through you because it has no cross term with the gauge field for E and M. Anyway, so yeah, there's lots of different candidates. There's WIMPs. There's also Primordial. This is not in favor. So the one I kind of
Mattos.
The primordial black holes.
Oh, the black holes. Yeah. Oh no, I like to speculate.
Yeah. So basically, early universe. If there is an inflation field, the Higgs will couple to the inflation field and give you perturbations within the field that will result in the production of primordial black holes after inflation is turned off. How does inflation get turned off? That's a great question. That's an unanswered question as well. But so the after some time, after some time, inflation stops and we get our locally observable universe. The Higgs decouples from that, but there are perturbations in the background field that create black holes. Now, these black holes, you're like, oh, that's kind of scary, thinking that it could be a candidate for a candidate for dark energy or dark matter. Sorry, excuse me. But these black holes kind of exist you've got the stellar black holes that exist for a very long time. You have Planckian scale black holes that evaporate very quickly. And then there's this Goldilocks zone of black holes that are semi-stable that exist for a much longer time. That's just kind of why that this is kind of falling out of favor, because the precision measurements that they're making make this more fine-tuned. But there's always a possibility. And so the event horizon is so small that you would not interact with it, because this is going to be less than an Earth-sized black hole, which I'm not saying Earth as an Earth. I'm saying Earth as if it were compressed to beyond the short shot radius of Earth, which is
In terms of
very,
mass, the mass,
and very, very, very tiny. But those would not interact with you. But eventually, if that was the case, then eventually they would evaporate via Hawking radiation and just disperse all the way down. So there's a little bit of a fine-tuned argument with that. You know, we're going to be talking about
evaporating black holes.
Yeah, we're going to be talking a lot about like models that have to be fine-tuned, and what that really means is that, you know, there will be some decimal place, like 43 decimal places in, 63 decimal places in, and then the theory has to be fit to such a precision that you would have to basically subtract off to get the rest of the piece out. That's what fine-tuning is. And there's some arguments for and arguments against that the universe is some type of there's a naturalness in regards to the universe, or that there's some that argue anthropogenic reasoning to kind of fit it in, and we'll talk through that when we get to the dark energy. But
dark energy. But I mean, the thing is, like, so through measurement and observation, you know, we see gravitational lensing of light around galaxies and clusters and things like that, and that lensing you can also it doesn't reconcile, like, sometimes with the mass that is estimated to be in those galaxies. So there are other things as well that kind of point to this. So there's quite a few things, like you mentioned before. If you have this cosmic microwave background radiation, which is red shifting, implying that the universe is expanding and that we had a big bang, and you could speculate on what that means, but also that the universe is not only expanding, but that expansion is accelerating. Then it starts to wonder, you know, what is driving that expansion, and then that's sort of the dark energy aspect of this, is that not only do we have a bunch of missing mass, we also have a missing repulsive force, which is sort of the anti gravity, if you like, the sort of the repulsion, the pushing apart of not just of matter, but space time itself. So there's sort of, it's good to establish that sort of missing mass, you know, to coin a phrase, the 85% of the matter that's unaccountable by measurement, but also to sort of consider that of that sort of total amount of matter, if you're talking about the mass energy of the universe, that only equates like for about 30%. So if like 5% ordinary matter, 25% dark matter, there's still 70% of the energy which is attributed to this dark energy. So the ramifications of this are huge. Like, I feel it's sort of understated a little bit in popular science and in other things, and, you know, people look around the world at all sorts of things, but they just accept that there's this huge paradox and sort of absence of explanation as to what's going on here.
Yeah, so we've kind of talked through dark matter. There are alternative theories to dark matter, though. Those galactic. Before moving on, just briefly.
Sure. Yeah.
So there are some there's some alternative there. Yeah, those are candidates. You know, supersymmetric particles, axions. You know, like I said, those are various potentially additions to the standard model, or minimally, maximally supersymmetric standard model, if you want to look at it that way. The problem, you know, again, experimental data is we're kind of the more data that we're collecting, the smaller those parameter spaces are looking within the TeV range at the Large Hadron Collider, and that we may have to push this up. there, yeah. So it gives, people say, well, why do we spend so much money on like a particle accelerator and have to spend all this effort to do it, to do these experiments? It, all these models are essentially the best guess that we have working within the frameworks that we currently understand. And then, the budgetary constraints and everything else kind of play into what's the target energies. And so
I can't believe that people would ever question why we spend money on this stuff. Like this is like understanding the nature of reality and where the universe has come from and where it is heading. And it's like, if we can smash a bunch of atoms together and try and see what comes out, I think that's a very human thing. Like let's see what we can, if we can reproduce these things.
Well, I mean, Fermilab, the updates on the Fermilab collider, they still can't seem to get that done. And then when I was in high school, the superconducting super collider was canceled. Like it was automatic. It was ready to go, full funding. They built buildings, everything. And it was the science community, because so much money was getting pumped into that it was diverting funds from their stuff. And so it just fell flat. And I'm like, this is crazy. This is insanity. But anyway, like I said, there's many candidates for it. Like I said, from a particle theorist point of view, there's an abundance of theories. And so, there's even stringy inspired models that you can consider. And so how would they, one of the ways that they would be able to potentially detect this at the LHC or the next generation is that basically when they would do a full energy calibration, if there's missing energy, it would imply it's the Fermi trick, where there is missing energy, and it's the neutrino was discovered by Fermi by just doing an energy evaluation of the decay, and he was like, oh, there must be something else, baby neutrino, or baby neutron neutrino, because it's it's chargeless, so it didn't interact with the detectors, but it and it wasn't the direction wasn't changed, but there was enough energy that it was essentially just inferred discovery by that.
Yeah.
So we understand those systems. We understand neutrinos. So this would be something like different, and we would, so they're accounting for the backgrounds are very well understood. The energy backgrounds are very well understood, and so if there's any missing energy, that's a potential dark matter candidate.
So when you get is it antimatter annihilation, when you get like electron positron annihilation, that sort of stuff, and you get like a gamma ray and a neutrino, like that sort of stuff?
Photon, yeah. Depending on what the scattering angles are, or there's the kinematics of the event, but electron goes to two photons to preserve parity.
And so because you've got this vacuum energy, because you've got this this quantum foam as well that's going, the virtual particle pairs that are sort of popping into existence and then annihilating. So those annihilations must be producing neutrinos as well, and that's happening.
It's happening everywhere. I mean,
I can't describe how many of those interactions are going on, because you have to consider the scale of the universe and how many of these things exist in the quantum foam.
Right.
But it's a lot. It's a lot.
Yeah. So let's first take a step back, and because we're kind of moving away from the dark matter discussion.
Sure. Yeah.
When Einstein wrote his field equations, he had a term. People started trying to solve potential scenarios, and one of the scenarios, though, Friedman Walker team discovered a model of the universe that was that if you applied the standard equations with dust, you got a collapsing universe. And Einstein thought, that's obviously not what we observe. And so he added a term in that was because Einstein believed in a static universe. And then that term ended up causing the solutions to basically have a static form. And then Hubble made his famous observations that the universe is indeed expanding. And so they took it away. That term gets dubbed his greatest blunder. Hopefully that's
the greatest blunder of his career. He said that. Yeah.
Right. So this is the cosmological constant. Right. This is really the measurement of the property of space-time. But it turned out that in the 90s that term was actually really needed to explain the expansion of the universe. And so a fellow a German by the name of De Sitter, like I said, you make certain assumptions and you can calculate exact solutions. And so De Sitter was playing around with that cosmological constant idea, and he was like, this is an accelerating, basically an exponential accelerating universe. And it turns out to be that's the case. And so lambda, the lambda term that's within that the field equations, is most likely the best candidate for dark energy that we have. Now, the distribution of it is it homogeneous? We don't know. There's measurements. The cosmic microwave background. They're continually looking for asymmetry or they're looking for variations within the cosmic microwave background that indicates whether or not some of the underlying assumptions are correct. But in that, this is where some weirdness starts to happen. So we know that for a static, so basically, if that's really the case, that we have a cosmological constant, it gets quantum corrections because it's in a Lorenzen variance tells us that the vacuum of the energy momentum tensor, which is basically in Einstein's equations, you have geometry is equal to energy, the energy momentum tensor or energy stress tensor. So matter tells space how to curve, space tells mass how to move. That's a term by Wheeler, or a phrase by Wheeler. But anyway, if you have a Lorenzen variant, it means that the vacuum of the energy tensor must take a particular form, and it gets a correction once applied to quantum effects. Now, the particle physicists can tell you that the vacuum, when we say vacuum, what would you think? It's empty, completely empty, and that would be true. But if you apply the laws of quantum mechanics to it, it's not empty at all. And you can calculate the energy of the vacuum. So the energy of the vacuum is not zero. Now, but this cosmological constant is very, very small. Let's say 10 to the minus, minus 43, something like that in the appropriate units. So it's very, very small. But if you calculate using, if you calculate the quantum effects, you're off by an order of magnitude that looks like 10 to the 120 23, depending on which models that you look at. So that's massive. It's a massive difference. So something else is going on. But quantum effects also, and I guess that 120 is, if you just consider free fields, which is not correct, but if you include the QCD vacuum, it's a little bit different. But the effect of quantum, hold on, check my notes. As I said, I'm not a, this is where I'm going. So if you look at it, if you look at the quantum corrections, it would require that you would cancel a term to about 41 decimal places, if that is truly correct. And so that's what they start talking about, a fine-tuned argument. There's also, so the presence of this cosmological constant now that this dark energy is representing, and that's when they talk about lambda CMD. And there was some controversy a couple of weeks ago about this, because if you look at the observations that were made and you apply different models, the universe is about twice as old as it was. So I have a friend that's on the review committee for the lambda CMD, and they were denied from seeing that data and seeing the model applied, because they're supposed to do like double blinds, and it's very, when they're testing these models, I mean, they've got, it's like clinical. It's pretty fascinating to look at. But it also indicates that it's impossible to find field equation or exact solutions to the field equations, because the original symmetries that Einstein was working through tells you that that you would have to have a fine-tuned universe, and that in itself, to me, like I said, there's lots of arguments you make for fine-tuning, for naturalness, for anthropogenic, and anthropogenic just means like the universe is the way that it is. Because we're here to make the observation, or make the ask the question,
to be aware of it. Yeah.
To be aware of it. And there's many forms. There's a strong form. There's a weaker form. But that in itself gives you a paradigm to kind of work through, to kind of put bounds on this. But honestly, for me, because gravity, there is no, a lot of the assumptions when you're talking about like how fine-tuned does it have to be, that's assuming that that general relativity is correct down to the Planck scale. But we have no way to really tell that right now, because there's no quantum field, complete field theory of the quantum scale of gravity. We have ideas, but the theories are incomplete. And like I said this last week, nature is hiding this beautiful puzzle right in front of us. And the best tools that we have at our disposal is kind of, it can't penetrate it. So it's just like, it's awesome.
This is your name.
This is
your
saying.
namesake.
Like there's
namesake, the graviton.
The graviton, right? Right. But I'm like, it's a beautiful puzzle. So, but anyway, so dark energy is even understood even less than. So, like I said, there's some, Weinberg had a beautiful paper, and if you, I'll put a link to it. It's technical, but he makes some arguments with the fine-tuning argument. He also makes some. He published in like '89 of this review of the work that had been done before. There's also, if supersymmetry is found, again, We haven't found it. We haven't found the experimental evidence yet. We have strong theoretical evidence that it could exist. And so supersymmetry has a potential to lower that fine tuning down. There's some other string models that Witten worked on in the 80s. Again, it's a shot in the dark. All these theories are shots in the dark. They're based on good principles, but there are consequences of those principles that may or may not represent reality. And it's a beautiful thing. And I think at this point, it's probably good to open it up for any questions, because we can go into like uber deep on this stuff. And
yeah, 100%. I think questions are always appreciated. And yeah, there is a point where we start to cross the boundaries of physics and start to enter the philosophical, because some of the explanations you can come up with, some of these ideas are quite fantastic, and it's like it's easy to make conjecture without having any experimental backup, but it does tend towards the realm of science fiction, without in the absence of measurement.
Right. And this is actually one of my main critiques of string theory. So string theory predicts that the cosmological constant actually has the wrong sign on it. So the stable vacuum, the 10 to the 500 vacuum, which is known as the landscape problem, it's where the strings can actually exist. The cosmological constant is the wrong sign. So if you get so there could be modes in which that I've seen models using I believe F theory or some derivative of M theory that that will kick modes up into the positive range, but they're not. It's not satisfying. It's not very. It may be right, but data does the data support it? I'm like, I also struggle whether or not it is a way to quantize gravity. You get a spin 2 field that is representing allegedly representing a graviton, even though I'm starting to kind of reconsider those notions right now in my own thoughts, kind of going back to some earlier work I was doing in grad school. But so I think we're a long way away. I think my children, my children's children, my children's children's children may not fully grasp what's happening at the quantum, once you get to Planckian scales. But what I was saying, what I am more optimistic about is that the nature of dark energy,
yes,
will probably be revealed once we have a complete picture of the of that. And the mathematics, and in reality, the mathematics is probably not invented yet.
And that's the limitation in our mathematics. And as much as I've got a degree in pure mathematics and I love it. There is limitations, and we do. And I've said this before, as physicists and mathematicians, we tend to just make the maths work. We go into another a complex Argand plane, or we start to use tricks where in higher dimensions where we go, oh look, I can get the right solution. Here we go. And then at the end of the day, if it is true, because you use complex numbers and things like that in physical measurement, and without it, you won't get the right answer. So it does work. It gives you a solution. But then to actually ask the question, what is this complex plane that we're dealing with, well, it's just a mathematical way of representing reality. It doesn't, it's an approximation to reality. It may not actually make sense to us. So the mathematical tricks are always there, and so that begs the question: is this a limit in human understanding? Is this a limit in our mathematical tools and mathematical models? And is this missing mass really? Is it really missing, or is this a flaw in some of our models?
Right. I mean, there are like I said that before. There's alternatives to to these pictures as well. Modified Newtonian dynamics, and its relativistic counterpart, the f of r, which is literally a function of the Riemann scalar uh, theories, both with various problems and both with Mond will eventually, I mean, if you apply Mond to certain structures, you still have to have dark matter. And so f of r, and then f of r has like Ostrogradski instabilities. And so when you quantize it, so basically Mond is basically that Newton's laws or Einstein's gets a correction at a certain distance. There's a distance scaling in those theories that they're not solar system corrections, but they are like galaxy size corrections. They're just like, why? But again, they'll say, well, these are fine-tuned models. I'm like, so they're not fundamental. Okay, got you. Then they'll put the point and say, your models are not.
Yeah, there's something. Yes, there's an inelegance. I think there's an inelegance where you can kind of say, oh, look, this only works at these scales, and then at these scales, it's like you kind of feel like they're both approximations if you can't get it to work at all scales.
So I started out my early career. So this is kind of where we're heading and where we were. So I was in my early grad school days, I was heading down the path of becoming a string theorist. And when string theory started to make anthropogenic, in which I know Weinberg, I knew that Weinberg paper, but when string theory like is supposed to be the theory of everything, allegedly, starts making anthropogenic claims, I'm like, it turns my stomach a little bit, but it could be right. Like I said, I may not. I could definitely be wrong. I mean, and I've met Ed, and I've seen Ed destroy their career at a conference one time, and I was like, I will never confront that man. Ed Witten. Anyway, so let's open it up for questions because I have to get off here in a couple of moments.
That's cool. That's cool. Also, like if no one's got questions, I think it's always good at the end of these spaces to open it up to the sort of some of the more fantastic ideas. So, we talked about the weakly interactive massive particles. And it makes complete sense. We're particles streaming through us all the time, and we've done measurements on neutrinos and things like that. So, and then you've got the massive compact halo objects. So there's all sorts of other candidates for dark matter out there, which are sort of. I think people can reconcile the idea that there are just stars out there or black holes and things out there that we just can't see through our electromagnetic vision, so to speak. And so that doesn't really. I don't think there's a huge paradox there, but the paradox with the expansion of the universe and what's driving that dark energy, the expansion that's accelerating of space-time, I think that there's something about that just speaks to everyone that kind of says, well, hang on, do we really know what's going on here? And there's ideas. I wanted to get your idea of about quintessence. and there's all sorts of, science fiction-y kind of ideas about dark fluids and things like that, or even just, the idea that if you have a black hole white hole pair, that this expansion could actually be driven, like we could actually, like the Big Bang could be a white hole just pushing, expanding outwards, which is the sort of like the black hole white hole sort of pair, so to speak, like a universe anti-universe pair, where one universe flows forward in time and the other flows backwards. You can get some of these Einstein field equations to work in some of these science fiction-y ideas. But yeah, so I guess that's one for you. Like, what do you think about quintessence? And also, what do you think about this whole white hole driving the expansion idea?
So quintessence is another one of the model. It's a scalar field model that is presupposing, and actually, so the general inflation of the universe could be have began, with the inflationary epoch. Could have began with like a quintessence model. Again, these models have not been. You have to basically fit the model to get it to work, and the observations, whether or not you have one, it could be a spurious field or not. I mean, I think if memory serves me, I'm not. That model has to be tuned to the saying that the excitation of that field, the mass excitation is like 10 to the minus 33 EVs. So very, very small mass excitation for the quintessence field to get the slow rolling inflation to work. And
Yeah,
so,
yeah.
it is a possibility. No one under no uh, Goof. Is it Goof? Grenade? Alan Goof was the inflationary model, and so quintessence and those inflation models are kind of are kin, are related. And so, as far as the white hole, um, I I I don't I I don't really have an opinion about that yet. I I, I was listening to I I have to go back and reread Penrose's paper on his model of what the early universe was. His notion is that the early universe and the late universe are in the same. Uh, he uses some conformal arguments to make the claim that the early universe, late universe look the same, and so basically you have photon fields. Uh, Maybe it's being driven by there's a white hole solution in Schwarzschild. I don't know. I mean, I'm
Yeah, it is
I'm kind of
speculative
neutral
at
to
best.
those, and actually, those kind of theories may end up, and I'm almost, and this is going to sound somewhat anti-science, but those models may always be pure speculation. And I don't think
Yeah,
that my colleagues would go that way, because if you have multiple models that give you the same observational result, basically what we see, how do you distinguish? How do you distinguish them? The science, real science. I'm not talking like pseudoscience, social science, whatnot.
yeah.
It makes specific, precise predictions.
Sure.
And if the prediction is as precise as you can make it based on the observation, you may not be able to distinguish them. And so
Mm.
for me,
But so
I don't know.
I see exactly what you're saying. I see exactly what you're saying. But I also think that, it's courageous for us to hold, in science, competing theories and consider them until we can kind of eliminate them. So even though sometimes these things can be a bit science fiction-y, it's okay to sort of to at least invest some mental energy on
Oh
these
no,
things.
oh, I absolutely believe that. But I'm saying I don't know if you can't distinguish them. That's my point. It's like if the
Okay,
observation
yeah.
and
I
the
s-
and matches multiple models of how
yeah,
things work.
yeah,
Um, Again, I think a lot of the mystery that we're lacking is still, is buried at 10 to the minus 34 centimeters. I, and nature is a cruel. Is not cruel. I mean, it's kind of cruel that it hides its most precious pearl. And so once we have that, I think we're going to be able to distinguish a lot more. Whether or not 3+1 is correct. Do we live in 3+1
yeah. Higher
space-time
dimensions,
dimensions,
or
or do we
yeah,
actually live in, a 10+1 or whatnot, whatever M theory, compactified M theory
yeah.
looks like.
Oh, and
Um,
we can maybe go into that like at another stage, or maybe the next one or whatever. We can talk about this concept of higher dimensions and things like that. But I guess my point was also like, so say there was always this classical idea of an ether back in the day, and then it was actually at some point the Michelson-Morley experiment, where they actually managed to disprove the presence of the ether, and like then there's things like gravitational waves where people theorize that you could have these ripples in space-time, and then LIGO found these measurements, these chirps from coalescing black holes. So there are, even though as we stand on the shoulders of giants in science, I feel like there's always room to kind of speculate. And so hopefully there will be experiments that can disprove some of these things or prove them, and so that idea, the quintessence sort of field thing of the permeating space, has kind of got an ether kind of feel about it, I must admit. But maybe
all
there's a
of it
way that
does,
they
though.
can.
The quantum vacuum itself, if you really think about the quantum vacuum, it
Yeah.
has a very ether feel. And the Michelson-Morley experiment is a null result.
Okay. I thought it
So
disproved it.
no, so you wouldn't be able to, kind of going back to what we were discussing before, it did not reject the null hypothesis. And so the null hypothesis is that they could not, basically could not detect an ethereal
Right.
motion.
Yeah.
But
I see what you're
in
saying.
reality, if you probe down further enough and excite the quantum vacuum, which is what they do at the particle accelerators, when you collide collide the various particles, you're exciting the quantum vacuum. And so,
100%.
is
Yeah.
it is it ether? No, it's not superluminal ether in the way that they
Yeah. In that
presupposed
sense.
it, but it is not
Yeah.
an empty vacuum. As
Yeah. And so
so
can we
like I said,
tap
that's
in?
why I'm
Can we
like, it's
tap
the
into that
most
energy?
famous
Yeah.
null result. So the null hypothesis not rejected doesn't mean that it's not,
Sure.
you know, it's just that the
Yeah.
experiment wasn't designed to probe down in that kind of range.
Yeah, yeah. And so
You
that
see what I
that
mean?
idea of tapping, 100%, yeah. So you can't prove the negative. Like you've proven that it's not there, but you can't prove that it's or wait, you prove that you haven't found it, but you can't prove that it's
It,
not there.
in fact,
Yeah.
the vacuum energy itself, I mean, not the vacuum, the dark energy itself would imply that that space is not empty. And so
Yeah.
that, flat space time is merely an approximation, that it's such a
Yeah.
a small perturbation, small amount,
Yeah.
that the flat Minkowski background is a solution to Einstein's equations for when you're sufficiently far away from a massive gravitational field. But that in itself is still incorrect, because there's vacuum energy or dark energy present in that whatever region of space-time that you're looking at. So I'm like, it's just approximation upon approximation. We're trying to get at the truth. So
yeah. And so but like with that idea that, the null hypothesis, like say for gravitational waves, I mean, that would have been a point where they would have been, well, you can't say that gravitational waves don't exist, even though they hadn't measured them at the time. But you can't say they do exist until they did, and then now we can. So that there is
now we've measured,
point.
and now they've used the pulsar. That recent was it 3 or 4 weeks ago? I mean, my brain is just like mush as far as like time. But I think it was like 3 or 4 weeks ago that this massive 15-year study on these pulsar signals, where they were able to find gravitational waves that were tens of light years, so it would have been impossible to detect at LIGO. And so through the spinning of these black holes and things like that. So yeah, I mean, as our instruments get more and more sophisticated and more precise on what we're looking for, you can start asking those questions.
Yeah, and so that's kind of where I was going with that whole idea of these, like a parent universe with a black hole that has a white hole that spews into our universe into existence, or even, well, okay, yeah, let's just start there, and then so the infinite gravitational attraction of the black hole in the parent universe having a singularity, and infinite gravitational attraction, like then spewing out on the other side to have this gravitational repulsion. That idea of expanding space on the other side of a white hole that could just be our reality as we know it. It would require someone to detect the parent universe through measurement to prove that sort of thing. You know what I mean?
Yeah, or through inferencing.
Or at least,
yeah. So
because that's
another reason why that the measurement of the amount of dark matter present in the universe, the amount of dark energy, what the density is also important, because that kind of plays into the role of what the ultimate fate of the universe is. Is it going to continue to expand forever, or is it going to accelerate forever, or is it going to eventually become static at some point? I mean, no one knows.
Yeah, so
a lot of these
idea of
right.
Yeah. So the idea of like a big crunch, if all the mass of the universe was actually attracting each other, and then the universe would actually contract, and you would have this sort of this big crunch idea, and then once it hits that, and then it starts again, but the conversely, that if this expansion is accelerating, and you can have this big rip idea where the atoms themselves get so far apart because of the space in between them is expanding, that the electrostatic bonds, the strong nuclear forces, the things like that holds the atoms together, those interactions are no longer possible. And so even just in our time scales of like 5 billion years before Andromeda merges with the Milky Way, or the sun goes, supergiant, red dwarf or whatever, red giant, sorry, when the sun explodes, like in 5 billion years, like, so in our like time scales of things, it's like it's not going to make a difference. But there is a point where you can imagine people looking out into the night sky with whatever instruments they have, and everything just being so far away from each other that you just wouldn't even see stars. Like you wouldn't see anything. But then, of course, would there be a stable system for life to be there anyway, to observe that there is nothing out there?
Or do you just
So,
go to complete thermal fluctuations, and you have an infinite number of Poincare recurrences, where you have Maxwell brains floating around, where the universe is local pockets
yeah,
have changed.
local pockets. Yeah, that's really interesting as well, that you can have
Local
pockets
pockets
where
of
this missing mass is just in a pocket of the universe that's just so far out of reach that even if we, because and that is a limitation in our understanding as well. So we have to assume, this isotropy of, like, if we take some portion of the night sky and we say, oh, wow, we can measure, even with the James Webb, and we can do the deep field and say, okay, well, however many arc seconds of whatever, we can say that there's this many galaxies and this. So it could also be a resolution thing. The universe could just be stranger than we think, or it could be like some of this mass could just literally be in black holes, and the energy that's driving the expansion could be as a result of black holes, because there is limitations to our measurements beyond the event horizon. So I think that is probably more likely. But also, I kind of like the idea, like this cyclical idea. But also, the thing that appeals to me with the black hole, white hole,
there's
sort
some
of
loopy, or there's some loop quantum gravity idea or models that indicate a bounce.
oh yeah,
But again, like I said, it doesn't match data, so it
yeah,
starts to and
you start to get to the philosophical. Yeah,
well, not just philosophical. I mean, it just may just be wrong. If the observation doesn't match, or if the theory doesn't match the data, it could be just wrong, and that's why. Like I said, I could be very, I'll be very critical of my own field on quantum gravity research, but
sure.
quantum gravity research is it's hard, but very hard. But anyway, let's get to questions, because I do have to go.
Yeah, is there? Yeah, please. I think there's no one that's. Oh, Collector Miner. Sorry, is it speaker? Go for it.
Hey, par excellence, Graviton.
What's up?
How you going, man?
Hey, doing great. I treasure this moment of being able to listen to two brilliant men talk about stuff. And
oh, thank you, sir.
It's absolutely awesome, And my ignorance abounds here, so I appreciate the way that y'all have spoken. So there's some things I can actually understand, other things are beyond my grasp of expertise and everything. I had just a couple questions, and so one of them was just a deep appreciation for you guys, because I'm fascinated by this type of stuff. When y'all were talking about dark matter and dark energy, I was curious that when y'all talked about neutrinos, y'all didn't talk about them in their separate forms. As far as like I think there's like 3 different types of neutrinos, but y'all lumped them all together, and I was just curious why.
So that's really a high energy distinguishing trait. When there's a potential that there's a different type of neutrino that is considered a sterile neutrino that's not coupled to. So there's the electron neutrino, the muon neutrino, the tau neutrino, and those flavors are. Think about it. I think the easiest way to think about it is those correspond to various energies. So you will get an electron neutrino pair, the mu, which is one step up in energy from the rest energy of the electron, and then the tau is one step up. So the sterile neutrinos are not flavored; those are flavors. Particle physicists love different beautiful names, but they're not flavored. they're separate, and so that they would represent a separate field within the equations, and those are all fast. All of those are considered, because the rest masses are so low, and the interactions occur at such high energies with when you're comparing the rest mass energy to the total energy of the system, or I'm hand waving a little bit, but basically those are all relativistic. Dark
Okay.
matter is not. It's a heavier particle, and it's slow moving. It wants to clump. Neutrinos don't want to clump. They want to
Now,
travel.
dark matter and dark energy is non-observable, right? And so you only see the effects of it, or can measure
You
that
only
it's
see the effects. It doesn't. So there's
right,
no scattering
Yeah.
with light. Yep.
right. I was
So you might
curious.
see the lensing or something like that from an object, like the gravitational lensing.
Oh man, that's fascinating. That stuff.
Oh yeah, yeah. Some of those deep
Crazy.
field, if you look at the Hubble deep field or the James Webb deep field, the gravitational lensing in that is off the charts.
Yeah, I like what you were saying before. It's almost like pointing to a dark part of the sky, and hey, it's not dark. There's light out there. Something's going on, and we just might
Oh
not have instruments that are sense enough to see it all.
It's
yeah.
amazing. I was listening to so like I said, I'm not a cosmologist, but I have lots of friends that are cosmologists, and I was listening to a talk that was at the Perimeter Institute the last couple of months, and the level of precision in the modeling and the measurements that they can take at the various observatories to match the models, uh, it's staggering. I mean, it really is staggering. I mean, when I was in grad school, I mean, we always joke that if you were within 100 light years for cosmology, you're doing precision work, but they're really
Yeah.
pushing. Yeah, they're pushing that and pushing that those uncertainties way down, and the
Yeah.
models are very sophisticated. In fact, let me share this in a. I shared it on my Twitter page of one of the models that somebody was working on earlier.
Awesome.
Yeah.
Yeah, that would be good.
Yeah. The other question I had for you is that where did Einstein discuss dark matter or dark energy?
No. So he didn't discuss either one of them. In fact,
Well,
that's where the origin of the cosmological constant
that's not important. Yeah.
was placed in the theory in order for the theory, whenever applied to a universe model with like dust, wouldn't collapse. And so he believed that the universe was static, it was unmoving, it was unchanging. He believed
Oh,
kind of in an
interesting.
eternal universe.
Yeah.
But what was found is that that term is real. And so
Yeah. So
that's
that
one like
idea of the
stroke of
cosmological
luck.
Yeah, that idea of the cosmological constant is basically he's saying, it was the greatest blunder of his career because he thought that the universe was static. But as they found that the universe is expanding and that expansion is accelerating, now there's that need for that cosmological constant. So, yeah, that's really interesting that he kind of put it in there and then discounted it, and then it turned out that possibly he was right all along.
Too
So
funny.
if you look at that link that I sent from Andrew Potson, it basically shows you like a model, prototype model of the cosmological simulation where they're modeling uh, what dark matter that they're expecting based on their measurements. Now, none of these models. The other thing I found out, and I didn't realize, was that none of the models include baryonic matter. So they ignore baryonic matter is like the perturbation in the modeling, and so everything is basically the dark matter. So
Okay.
and this is where they were doing, and this is why I was like, when and my
It's
and
only
actually my
5%.
friend and I just had a discussion about it, so I already knew this, that they basically do a double blind, and this is why he's on this on these committees where they're basically like, yes, you can they do like double blind studies, and uh, because there's a lot of work involved,
Yeah,
and
I
then
imagine it's got to be critical. You know what I
oh
mean?
yeah, yeah,
You got to make sure
it's
that people aren't prejudging stuff and everything.
putting their own
Oh,
personal biases in it.
yeah.
Yeah, absolutely.
Well,
Hey,
like say for example, the cosmic microwave background radiation, like that's really well, like that's accurate to we're talking. It's like 160 gigahertz or something, but so that would be measurable to 9 decimal places or something like that, like parts per billion. But then when they have this anisotropy sort of mapping of all the there's other things that come into it where it's actually really interesting. Yeah.
I've dated myself a couple of times when I said that I was in college whenever when we discovered that it was accelerating. But I was in grad school when that the WAM that map
The mapping, yeah,
the
that's
W
really
map
interesting.
first
I think I remember that
first
too.
came
Yeah,
out. Yeah, I was
yeah.
first or second year grad student.
Mhm.
I can remember going to seminars about it, and I'm like, this is interesting, but I'm more interested in quantum gravity. But
I'm curious
it's
on the
not changing my path.
yeah. Hey, I'm curious on the acceleration. Is that uh, uh, is there a theoretical limit to how fast that acceleration can occur? Before
Great
we spread
question.
out.
Yeah,
I'm sorry.
that's a great question. That's a great question. Yeah.
These measurements
Keep going.
are
Keep going.
giving these So these measurements are giving you a limit on those on what the acceleration looks like. So the measurement of the of lambda CMD and dark matter are both giving you an answer to that question. So
So, collector mind, are you sort of wondering, when there's limitations on how fast mass can travel in our universe, like the ultimate speed of light? Are you
If
saying
it
that is it possible that the expansion could be faster than the speed of light? I think the answer is yes.
Wow, wow, yeah.
Yeah,
I mean, it's
because
just
this,
about if it's keep on accelerating, man. Is that what's the limit? You know.
yeah, Graviton might be able to explain this better than I can, but the space is not confined by that boundary, because the space is what holds it, it's what
Well,
contains the
space, yeah. So space is what the space time is telling is the ruler, and essentially the ruler in which things are getting measured. And so the speed of light is getting measured within that expansion of the ruler. So anyway, yeah, I'm trying to say this in a non-technical way. So basically, if you look at a small enough region of of space-time, even if it's expanding locally, everything's still, if you were to consider, it's still moving at the speed of light. I mean, the speed of light is still the finite speed that it is. But when you get an expanding universe, the ruler itself is expanding as well. So the measurements of the ticks of the clock change.
yeah, at the
And
same time. Yeah.
yeah. The ticks of the clock change. So does the ticks on the ruler change. So the speed of light is staying the same, the same rate. But
Yeah, so the speed of light is
there's
constant in all
no,
reference
we
frames.
don't
Yeah,
know
but
what, you know, we don't know what the ultimate fate of the universe is.
Right.
And I
It's
actually
going
find that
cool
kind of
or
comforting as well.
yeah, spread apart so far. We're all cool and can't see anything. black
thermal
sky, or
just
we can
thermal
track.
fluctuations, no
Yeah.
observations. The interesting
Yeah.
thing is that if we project ourselves, far enough in the future, that none of the observations that we've made that would have been able to determine any of these theories, nobody would ever believe, because they wouldn't have the data to support it.
Yeah, I assume that when we get
So we
a
live at a
space
unique time.
telescope, yeah, I assume when we get a space telescope or some type of electron microscope or whatever, and we think we've seen the smallest or we've seen the biggest, God will probably put up a sign and say, "Hey, you ain't looked hard enough. Come on, let's get on it."
Well, there's a boundary to what we will be able to see. There, you look back far enough, basically the universe is opaque. This is basically what I was inferring when we were talking about quintessence and various inflation models and things like that. The universe is opaque. It's
in the early inflationary, so at the early stages.
Early universe.
Yeah, so much dust.
Well, the density is so high. The density is so high. It's basically no light was, penetrating. So you can't, it's like
the primordial soup.
My dad used to tell me.
Yeah,
it's the example of. When I was a child, I would stand in front of the television. My dad said that I make a better door than a window, and I'm like, what? And he'd look at me and he's like, you're opaque, and I would move when he would tell me that. And so, you just can't. It's a barrier that you're never going to penetrate, no matter how good your telescopes are.
How far back is JWS look back?
I can't remember that off the top of my head, but
okay. Well, gentlemen, I'm sorry.
Yeah. No, go ahead.
No, I've taken up a lot of y'all's time, and I just wanted to tell you I was just absolutely fascinated listening to you two guys talk. It's just I know sometimes when I start thinking about some of that stuff after I read an article, whatever, my head just hurts. It's just so big and so grand, what's actually going on out there. And I'm thankful that we slowly over time have come to know and understand a little bit more of it. And it's like one of the great challenges that we have as men and women in life is look up, look down, look in, and get to see what in the world's going on, because it's just absolutely amazing.
Absolutely.
Wow, that's beautiful. Yeah, I love that idea. Yeah, that's and thank you very much for your kind words and for coming up and continuing the discussion, the conversation. And yeah, I think you're 100% right. I think there is a certain human aspect to it where it's like the pondering and the wondering why, the curiosity. And so I encourage it. I think it's great.
And I guess with that, we'll bring it into it. Thank you all for listening, and hopefully you come back the next time. We'll be discussing what we're going to talk about. I'd kind of like to talk about holography theory.
Oh wow!
Going back
that would be awesome.
Black holes. I've been thinking about that.
Cool. I think it's a good place to leave it. And yeah, I encourage everyone to sort of look up at the night sky and question and wonder why. And there's lots of information out there on this sort of stuff. So yeah, go down the rabbit hole and enjoy it.
Good night, gentlemen. Thank you.
All right. Thanks, guys. Thanks very much. I'll catch you later.